Enterprise AI pilots routinely boast 99% technical success rates in the lab, only to face total financial collapse in production. The standard industry reaction is to assume the model lacks horsepower, prompting organizations to quickly scale up centralized cloud compute. But compute power is rarely the actual bottleneck. The breaking point is physical routing, specifically the distance between the model executing the work and the user requesting it. This visual represents the core structural penalty, inference egress cost scaling. The heavy and tangled block on the left illustrates the friction of moving data out of a centralized network. Hyperscalers enforce a synthetic toll booth on this movement, charging between 5 and 9 cents per gigabyte every single time data transfers out of their architecture. For high-frequency, real-time AI workloads, those fractions of a cent scale exponentially, quickly outpacing the operational revenue those queries are meant to generate. Rapid AI margin erosion is never an accident. It is a built-in architectural tax paid directly to the providers of origin-dependent infrastructure. Alongside these financial tolls exists an absolute physical constraint governing all network transit: the speed of light traveling over fiber optics. A 3,000-kilometer round trip dictates a hard floor of 30 milliseconds in latency. No amount of software optimization can negotiate with that physical law. While geographic latency is a strict boundary set by physics, the hyperscaler egress toll is a purely synthetic constraint stacked on top of it. Bypassing these twin constraints requires structural decentralization. The compute must move directly to the data through EdgeInference. Shifting inference to the edge removes the physical latency floor, but it introduces a severe distributed systems engineering challenge that will define the next industry moat. Look at this amber pulse of light. As it travels through an industrial fiber optic cable, it struggles against friction. Data transit requires time. That friction multiplies when centralized factories attempt to serve highly concurrent geographic environments, like this Tier 2 Indian city, requiring intense localized routing to function. Organizations are uncovering limits of centralized routing on their balance sheets. Consider NASA's recent cloud agreement. After securing a $65 million contract, an internal audit revealed that unanticipated data egress fees could add $30 million to their yearly bill. High-frequency AI inference compounds this data transfer tax, byte by byte on every user interaction. Any real-time system relying heavily on a centralized cloud is paying an ongoing, non-negotiable tax directly to physics. Notice the absolute precision this robotic armature requires to place a delicate lattice structure. This is where delayed inference carries real physical weight. High-concurrency industrial vision systems, autonomous monitoring protocols, and physical robotics demand continuous data flow. These environments require sub-50 millisecond determinism to maintain accuracy, guarantee safety, and preserve operational continuity. Centralized cloud routing architectures inherently struggle to meet this requirement, introducing unavoidable transit delays that compromise the control loop. In industrial AI, delayed inference introduces immediate safety hazards and critical liabilities. To eliminate this lag, content delivery networks are quietly evolving into intelligent, decentralized inference orchestrators. This AI grid architecture drops heavy compute nodes directly into thousands of localized edge environments, drastically shrinking the geographic gap. These localized nodes are being equipped with highly optimized open-source inference stacks, specifically leveraging hardware like NVIDIA's Blackwell platform. Integrating this advanced hardware with deep edge distribution drops per-token production costs by up to 10 times. Real-world retail benchmarks show edge inference queries running 78 to 91% cheaper than centralized cloud alternatives. By forcing the compute to execute precisely where the data is generated, operators completely eliminate the origin-dependent egress tax. Moving compute to the edge respects physical constraints, but it creates the ultimate modern distributed systems engineering challenge. This grid visualizes the new moat, orchestration. Managing state across thousands of heterogeneous far-edge nodes requires deep discipline. Every node must securely rotate credentials and sync models flawlessly without continuous cloud connectivity. As failures occur, the orchestrator instantly resolves state breakdowns, maintaining network integrity. The orchestrator relies heavily on semantic caching to defend against expensive, redundant computations. Local memory at the edge identifies semantically similar requests and serves the result instantly, preventing the GPU from firing unnecessarily. It also monitors latency-aware routing, seamlessly shifting workloads to adjacent, healthy nodes the exact millisecond a localized hardware failure is detected. Competitive advantage rests in intelligent, resilient workload routing, which matters more than raw GPU density. To map the macroeconomic impact, compare the two long-term cost models on this graph. The left side demonstrates the centralized tollbooth model, where taxes aggressively erode profit margins linearly as traffic scales. The right side illustrates edge-native architectures inverting that gravity, trading runaway operational expenses for distributed, highly predictable execution costs. Enterprise organizations must adapt their internal FinOps frameworks to accurately track these decentralized assets. Evaluating infrastructure solely by the hyperscaler metric of cost per token is an accounting trap. It entirely ignores the massive financial cost of physical distance. Teams scaling AI effectively are adopting new ROI metrics: cost per successful outcome and latency per business event. Egress dependency ratios and cacheability rates are the new core key performance indicators for enterprise operations. Severing the reliance on centralized nodes reclaims operational control. The transition to the edge requires building with intent. This represents the quiet architect philosophy. True technology does not perform intelligence loudly. It reduces risk and restores safety silently. A brilliantly engineered prompt without an operationally sound architecture behind it is merely decorative intelligence. True AI scale requires an orchestration control plane that respects the laws of physics, eliminates synthetic tolls.
Enterprise AI pilots boast a 99% technical success rate in the sandbox, but the moment they reach production scale, they consistently collapse financially. As user volume grows, organizations discover a severe cost-revenue inversion. Cloud inference costs and data transfer fees begin scaling exponentially faster than the operational revenue the application actually generates. The industry often misdiagnoses this failure. Teams assume the system needs a more efficient open-source model, a better application wrapper, or sharper prompt engineering. But the actual bottleneck is not the reasoning capabilities of the model. The bottleneck is the infrastructure routing the request, and the vast physical distance stretching between the centralized data center and the end user. Real-time AI is breaking under two specific constraints: the non-negotiable physical propagation speed of optical fiber and the synthetic financial toll of centralized cloud egress fees. To solve this, the strongest builders in the market are quietly moving the compute directly to the data. They are shifting physical AI workloads to EdgeInference nodes, utilizing global content delivery networks. But distributing intelligence to the far edge creates a severe new engineering choke point. Managing dynamic state orchestration across thousands of scattered nodes requires strict distributed systems discipline. Surviving the transition to production AI requires treating inference as a rigid problem of physics and network routing, rather than an exercise in software design. This map tracks a query from a centralized cloud in Singapore to a user in Nagpur, India. The timer calculates physical transit through optical fiber at roughly 5 microseconds per kilometer. This delay establishes a strict, non-negotiable latency floor. Layered directly on top of this physical delay is a synthetic financial toll booth. Every time a response leaves that centralized cloud, the hyperscaler charges you. Standard egress tiers extract between 5 and 9 cents per gigabyte of transferred data. When an AI workflow processes thousands of high-frequency requests, computer vision, voice agents, real-time fraud scoring, these microtransactions compound into a massive structural drag on unit economics. This architecture forces origin-dependent lock-in. A small number of centralized cloud incumbents benefit directly by capturing exorbitant recurring fees simply because data is forced to travel long distances. We can observe exactly how fast these fees destroy budget predictability at enterprise scale. Following a $65 million annual agreement with AWS to host scientific data, an internal audit at NASA revealed a severe miscalculation. Unanticipated egress fees were projected to add an additional $30 million per year to their bill. That margin of error is predictable. It is a known architectural tax hidden deep within the structure of standard cloud-native designs. Routing high-frequency AI workloads to a centralized cloud means voluntarily paying a heavy tax to both physics and hyperscalers on every single query. The tolerance for this latency varies wildly depending on the workload. A text generation chatbot taking 2 seconds to reply is an inconvenience, but in industrial robotics or safety systems, a delayed automated halt command results in a catastrophic physical failure. Factories handling hazardous materials and heavy machinery require deterministic sub-50 millisecond control loops. Centralized cloud routing is inherently non-viable here because round-trip delays are dangerously unpredictable. We see the same rigid requirements in high-concurrency digital environments, particularly in mobile-first markets like Tier 2 Indian cities. Financial institutions in these regions demand split-second determinism to execute personalized fraud detection and marketing recommendations in the exact moment a user logs in. In these specific markets, an added 100 milliseconds of network delay breaks the user's immersion, compromises security scoring, and directly destroys conversion rates. Regulatory compliance accelerates this pressure. Emerging data sovereignty laws increasingly mandate that inference occur physically within local borders. This automatically disqualifies the use of offshore centralized data centers. For agentic, real-time, and physical AI systems, ultra-low latency determinism is the baseline requirement for the system to safely exist. The architectural solution requires bypassing the hyperscaler entirely, deploying inference at the extreme edge of the network, as close to the user as physics allows. To achieve this, global content delivery networks are evolving from static file pipes into highly intelligent inference orchestrators. This comparative chart illustrates the resulting cost arbitrage. By executing retail workloads at the edge rather than the central cloud, operators drop their per-query costs by 78 to 91%. Instead of relying on a single origin node, the architecture dissolves outward. The workload routes across a distributed AI grid containing over 4,000 localized edge nodes, powered by optimized open-source models on next-generation hardware. Cost drops further through semantic caching. When an edge node recognizes a repeated prompt, it serves the answer instantly without computing the workload from scratch. The system applies intelligent routing. It automatically matches lightweight workloads to cheap edge compute tiers, strictly reserving heavy premium GPU cycles for complex multimodal tasks. This is the exact distributed architecture that rescued web media performance in the early 2000s, now successfully applied to AI tokenomics. It also eliminates the idle GPU problem. Companies no longer pay flat hourly rates for massive cloud compute regardless of actual utilization. By utilizing localized hubs, operators are achieving up to a 10x reduction in their raw cost per token. Erasing the egress fee divorces the actual cost of producing an AI token from the inflated premium charged by hyperscalers. This edge orchestration layer provides early adopters with a massive arbitrage window. They scale their margins aggressively, while competitors bleed out paying origin-dependent server costs. Moving compute to the edge definitively solves latency and egress. However, it introduces a severe operational reality. The new structural choke point is distributed state management. When an application attempts to sync across geographically separated, heterogeneous hardware, it risks flashing with errors tied to version skew and cache coherence. Maintaining strict model version consistency across thousands of nodes is exceptionally difficult without a live cloud connection. Furthermore, distributing API keys, certificates, and secrets must be done flawlessly across disparate endpoints simultaneously. State synchronization becomes critical in multi-turn AI interactions. A user's second prompt might be handled by a completely different physical node than their first. The vast majority of enterprise teams and system integrators lack the distributed systems engineering discipline required to build this routing logic themselves. If governance is not built directly into the architecture from day one, the cost of auditing the system and executing emergency rollbacks scales right alongside the network. The true technological moat in AI is no longer the model. The model is commoditizing. The moat is the orchestration layer, capable of routing dynamic inference securely at a global scale. AI infrastructure is a rigid physical reality, bounded by fiber optics, geographical distance, and economic scaling limits. It is not a frictionless software environment. Infrastructure architects must change their primary metric. Do not measure the isolated cost per token. Measure the end-to-end cost per successful outcome under a strict service level agreement.
Map the round-trip network latency and the hyperscaler egress fees for a single workflow in your current environment. Then, compare those numbers against routing that same workload through a CDN-hosted edge node. True restorative engineering builds infrastructure that executes flawlessly and silently. It prioritizes keeping users safe and keeping systems operational over performing intelligence loudly. The defining architectural shift of the next decade is moving away from massive centralized AI factories. The future requires weaving a distributed grid, placing intelligence precisely where the